the reason when the external light is stopped, the fluorescence of chlorine sulfate is stopped, but radium doesn't. Why, ma'am?
It may be related to the principle that is involved in one kind of spectroscopic instruments. Do you know what it is? Fluorimetry. It is fluorimetry. So we can explain the same phenomenon with the help of one diagram, and that is called as Jablonski diagram. We all know the principle involved in fluorimeter is emission. In this, here the sample will observe the light radiation and they will move from ground state to excited state, and while returning to the ground state they will emit some radiation, and those emitted radiations can be emitted in two types. One is fluorescence and another one is phosphorescence, and also some type of radiationless transition will also happen. So we can learn that with the help of this Jablonski diagram. So this Jablonski diagram will be explained with the help of two types of excited states and one ground state. And the ground state is called as singlet ground state because here the electrons will be paired and they will be having opposite spin, and it is indicated by S0. And another excited state is S1 and then S2, and they are called as singlet excited states because here the electrons are unpaired but they are still having opposite spin. And another one excited state is triplet excited state. Here the electrons are unpaired and they are having same spin. So with this three types of excited states we can explain the Jablonski diagram and the electronic transitions. In fluorimeter, the fluorescent compound, that is the fluorophore present in our compound, will absorb the light radiation from light source, and after absorbing the light radiation the electrons will move from singlet ground state to the singlet excited state, and since the excited state is not stable they will emit to the ground state, and those emission can be categorized into different types. So one type is radiation transition and another one is radiation-less transition. And in radiation-less transition, in between these two excited states, these both are called as singlet excited state, but they are having different energy levels. So the electrons that are present in S2 will move to the S1. That is called as internal conversion. So this especially happens between the molecules, that is between one molecule, and it happens because the molecules will undergo some vibrational relaxation or collisional deactivation during the process, and that is the reason behind internal conversion. And some vibrational relaxation will be there because the molecules are having some bonds, and those bonds and the electrons present in the valence orbital will produce some vibrational energy along with the electronic energy, and because of that the vibrational relaxation may occur, and these two are especially called as radiation-less transition because there is no emission of radiation, only the energy is lost in different forms, and some of the energy is also lost in the form of heat. And after this the electrons will go to ground state in two types. There are two types of radiation transition, and in first type is the movement of electrons from the singlet excited state to singlet ground state. Okay, while moving from this state to this state, the electrons will emit some light radiation at a longer wavelength. So the light radiation is observed at shorter wavelength and they are emitted at a longer wavelength. So the absorption will take place at femtoseconds, that is 10 to 15 seconds, but while emission they will last only for a few minutes, like a few seconds. It lasts only for a nanosecond. So this movement of electrons from singlet excited state to singlet ground state will emit a radiation at longer wavelength, and that is called as fluorescence. And there is another type of transition also that happens because of some special mechanism or special environmental conditions, and which may be the presence of oxygen or low temperature conditions. And in those conditions the electrons will move from the S1 to T1. T1 is called as triplet excited state, and this movement is because of the reasons I said before, and that is called as inter-system crossing, and this inter-system crossing will happen for a nanosecond. This is the forbidden transition because we can see the electrons here both are unpaired but they are having opposite spins. Here the here the spin is same. So since the movement from S1 to T1 seems not possible, it is also called as the forbidden movement. And after this transition, the electrons will move from T1, that is triplet excited state, to the singlet ground state. And this phenomenon is called as phosphorescence. Okay, because they are showing some delayed fluorescence which may last for about microseconds to seconds, which will be longer when compared to that of a nanosecond, that is fluorescence. So that is why phosphorescence is also called as delayed fluorescence, and this happens because the electrons move from triplet excited state to singlet ground state. So we can clearly see the difference between phosphorescence and fluorescence here, and it also can clearly explain why this phosphorescence and fluorescence occur. As you said, you asked earlier that radium is showing phosphorescence, but the quinine sulfate is showing fluorescence. So we can clearly see that quinine sulfate will show its fluorescence only for a few seconds, but whereas the radium can show its fluorescence for about microseconds to seconds, which is actually longer than the fluorescence. So that is the reason the radium will produce its fluorescence to a much longer time when compared to the fluorescence, even when the incident light is cut off.